Okay, we're live.
All right, let's get started. Welcome everybody to the January 14th, 2021 press conference at 12:15 p.m. Eastern Time titled Galaxies and Quasars II. I'm going to be your host today. I'm Haley. I am the Astrobites media intern for this meeting and also an Astrobites author. I'm also a PhD candidate at West Virginia University. And today I'm joined by Susanna Kohler, who is the editor of AAS Nova, who will be handling the questions for this meeting. Tarini Konchandi who is a PhD student at the University of Texas A&M and who is also our AAS Media Fellow, and Rick Feinberg, who is the AAS Press Officer. So today we have 3 press releases that will be going out after or during this meeting. And yesterday's videos should be all webcasts on YouTube. So before we get started, a couple of ground rules. We are recording this briefing and streaming it on YouTube. Before we start, I'll give a brief introduction of the topic and the panelists. All the panelists will speak in their scheduled order, and then we'll go to Q&A. Attendees, please type your questions in the Q&A feature instead of on the Slack, and please write your affiliation and along with your question so we can identify you and who your question is for. You can also comment on other people's questions by upvoting them, which will raise them in the queue. We would not like the presenters to answer questions via text while other presentations are still ongoing. We will answer everything at the end of the Q&A. The attendees are welcome to chat with each other in the Slack channel. It starts with 000, but please put all of your questions in the Q&A. So the title of this press conference is Galaxies and Quasars II. We had a lot of exciting talks earlier in the week on this subject, so we're looking forward to presenting you with a little bit more. So today we have 4 speakers for this press conference. First, we will have Adi Foord from Stanford talking about discovering the missing population of dual active galactic nuclei with Chandra. Next, we will have Duilia Mello from Catholic University of America talking about the deep images of mergers, the DIM project. Next, we'll have Jordan Guerra Aguilera from Villanova University with his talk, The Magnetic Field of the Cigar Galaxy. And last but not least, we will have Alejandro Borlaff from the NASA Ames Research Center with his talk, The Multi-Phase Spiral Magnetic Field of the Whirlpool Galaxy. So I will turn it over to the first speaker.
Great, thank you. All right, hello everyone. My name is Adi Foord and I'm a PORAT postdoctoral fellow at Stanford University. Today I'm going to be telling you about some new discoveries that were found from analyzing a sample of nearby triple galaxy mergers and what we learned about supermassive black hole activity. So with the advancement of incredibly powerful observatories, we're starting to confirm the existence of black holes. Here I'm showing a schematic of how different detectors are sensitive to a specific range of frequencies and periods associated with gravitational wave events. With LIGO, we know stellar mass black holes both exist and merge, where the stellar mass black hole mergers detected by LIGO have masses between around 20 and 70 solar masses. From the Event Horizon Telescope, we have some of the first definitive proof that supermassive black holes exist. This is the first image of a supermassive black hole that was recently released by the Event Horizon Telescope, and the mass is around 6.5 billion solar masses. However, evidence for whether supermassive black holes merge will have to wait for interferometry in space, which we don't yet have, or data from pulsar timing arrays, which takes years. This is because the frequency of the gravitational waves that supermassive black hole mergers are expected to emit are outside the range of LIGO's sensitivity. Thus, observationally, galaxy mergers are actually some of the best evidence that we have that supermassive black holes are on a collision course with one another. This is because we believe that most massive galaxies host supermassive black holes at their centers, including our very own Milky Way galaxy, where they have masses between millions to billions of solar masses. However, 2 supermassive black holes on a collision course are likely to encounter a lot of barriers before actually merging. For one, they need enough gas to accrete at all stages of the merger in order to continue moving closer to one another. And even with enough gas, it's been shown that they may not merge within the lifetime of the universe. So this would mean that space-based interferometers and pulsar timing arrays would have no signal to detect from supermassive black hole mergers. And in the past, this has been dubbed the nightmare scenario. A system where 3 supermassive black holes are interacting may be able to alleviate some of these issues. The presence of a third black hole can make a circular orbit much more eccentric, which you can see in this simulation. The merger timescale is a strong function of eccentricity, and it's been shown that an increase in eccentricity can decrease the merger time by more than a factor of 10. Thus, triple supermassive black hole systems are an important and really interesting subset of the merger population. For our study, we created a sample of nearby triple galaxy mergers and used the Chandra X-ray telescope to carry out one of the first systematic searches for nearby triple supermassive black holes. X-rays are one of the most powerful ways to detect growing supermassive black holes, and with Chandra's excellent angular resolution, it's the best X-ray telescope to look for closely separated black holes that may be in the process of merging. We recently published our results in 2 papers that have been accepted to the Astrophysical Journal. Besides finding new triple growing supermassive black hole systems, we are also interested in measuring how many supermassive black holes were found in each triple galaxy merger and connecting these numbers to various environmental properties of each of the mergers. So our sample consisted of 7 triple galaxy mergers identified using the Sloan Digital Sky Survey, or SDSS, and I'm showing you those optical SDSS images here. The redshifts of these galaxies are between 0.03 and 0.08, which corresponds to distances between 400 and 1100 million light years. The nuclei within the mergers have separations between about 10,000 and 50,000 light years. We analyzed the X-ray emission of these galaxies, and here I'm showing the Chandra X-ray observations. As you can see with the X-ray data, it's not so clear what we're looking at. We analyzed each of the X-ray observations using a tool I developed while a PhD candidate called Baymax. Baymax can analyze X-ray observations and tell you how many X-ray bright sources the observation likely contains. This is very useful when you're searching for supermassive black holes in Chandra observations. The triple mergers had a wide range of supermassive black hole activity, and I'm showing you a few examples here. In the cyan circles, I'm showing the location of each detected supermassive black hole. So we found 4 new, previously undetected double supermassive black hole systems, and I'm showing the images for 2, which are most obvious to the eye. We also confirmed 1 triple supermassive black hole system that had been previously identified in 2020. Overall, we found triple galaxy mergers with anywhere between 0 and 3 growing supermassive black holes. Using available infrared observations, which are sensitive to levels of dust, we found a trend between the levels of gas and dust in these triple galaxy mergers. This is shown here, where as the dust levels of each merger increases, so do the gas levels. Each marker represents a different triple galaxy merger, and I'm denoting how many X-ray supermassive black holes were detected with the numbers next to each marker. This trend suggests that the motion of gas and dust are coupled in merging environments, and large amounts of both can maybe be efficiently funneled into the active central region. Interestingly, we found that 1 triple supermassive black hole had the highest levels of gas and dust, while the double supermassive black holes all had lower levels. Given that supermassive black holes grow and ignite through the accretion of gas and dust, it is possible that triple merger systems with higher levels of gas will have more growing supermassive black holes. In the future, this is something worth measuring with a much larger sample. So to recap, this study used X-ray, optical, and IR observations of supermassive black holes to study how supermassive black holes grow and what triggers this growth. We focused on a sample of triple galaxy systems, which are important for supermassive black hole growth and evolution via mergers. Analyzing the Chandra observations of 7 triple galaxy mergers, we discovered 4 likely and previously undetected double supermassive black hole systems and we confirmed one triple supermassive black hole system. We found that gas and dust levels are linked, and that the triple supermassive black hole system had the highest levels of both. Future work includes analyzing larger samples of triple galaxy mergers to confirm any trends. Thank you.
All right, can you hear me? I guess.
Yep.
Yep. All right. Well, first, thank you very much for attending the press conference. It's a pleasure to be here. I'm Duilia Mello. I'm a professor at Catholic University of America in Washington, D.C. So I'm going to tell you today why I think this project is actually a success story of the pandemic. So let me give you a little bit of background on galaxy evolution and why I came up with this idea. So it's been more than 400 years that we invented a telescope, but it's only about less than 100 years that we know that we live in a galaxy, the Milky Way galaxy, and that those tiny little fuzzy things that we used to call nebulae are actually other galaxies. And the person behind this incredible discovery is actually Edwin Hubble. And I highly recommend everybody to read the book, The Realm of the Nebulae by Edwin Hubble, where he gives the state of the astrogalactic field at that time that's being invented at that time. So he came up with this classification scheme of galaxies that we use until today. So this is what's called the tuning fork, where we have the ellipticals on one side and the spirals on the other side. And then he put it in the middle there, and that's a drawing by Hubble that says S0 galaxies. And he calls S0 galaxies very important stage in galaxy evolution or transition stages. We're not sure Edwin Hubble actually knew so much about galaxy evolution at that time. In particular, he knew that galaxies go to this transformation of morphology when they collide with each other. But he didn't know that there was evolution of galaxies, and he didn't know that S0s were particularly important. But S0s don't get so much attention in our days. I find them particularly interesting, in particular because if they are this important phase in evolution, we should actually be able to put it all together, the picture of galaxy evolution using them. When you look at the elliptical galaxies, sometimes they're not just red and dead as described, they're actually much more complex than expected. And this is the case of NGC 474, where we have the elliptical galaxy on the left side here. But then when you take an image with a CFHT telescope, which is almost 4-meter telescope, so it's a large telescope, you see a lot of debris, a lot of things caused by the interaction with another galaxy, and also maybe perhaps with another small galaxy that has been causing all these interesting features. So when we look at this gallery of interacting galaxies here by the Hubble Space Telescope from Aaron Evans and collaborators, we see major mergers. So galaxies that are more or less the same size colliding with each other. And here we see one of the final stages of a merger. We are not sure actually what's going to become right after this, but we think it's going to be an elliptical galaxy. But does it go through that important stage of evolution that Edwin Hubble so much liked, called S0 galaxy? So we don't know. There are some simulations that tell us that elliptical S0 galaxies actually are formed, and I'm sure you have been looking at this little video here, by minor mergers. So it's a small galaxy, it's 10 times smaller than the massive galaxy that collides with that, and then causes all the strange features outside them that we call shells. So it's quite impressive that we are able to reproduce this kind of features in numerical simulations, and actually we do see them in the universe, those types of galaxies. So I decided that I wanted to expand more what we know about galaxy evolution in terms of connecting the dot with the S0s and the ellipticals. So in order to do that, I would need many deep images in order to see those debris outside galaxies. And those are very expensive, especially if you do a lot of galaxies in order to have a very important, very systematic analysis. So I went to a conference a long time ago and I met David Martinez Delgado, who had a project doing stellar tidal streams. So he was looking at this tidal tails that actually come out of spiral galaxies with amateurs. So those are small telescope by astronomer amateurs that are actually using their personal telescopes to do beautiful images together with David. So I thought, wow, I could do this with S-zeros and ellipticals, because, you know, that could be fantastic. But then I went to Brazil to a meeting of the amateurs, and I met Cristóvão Jacques, that he's an engineer, and he is famous for discovering near-Earth objects with his telescopes. So I decided to ask him, so do you want to observe galaxies? And he said, no, galaxies are hard, galaxies are too small. So I told him, well, I've seen those deep images done by the team with David, and he said, well, now let's talk about it. But then 5 years passed and we didn't talk about it. But then with the pandemic, I was in so many lives and so many webinars that I met Cristóvão a couple of times, and I asked him, so how about our project? And then he said that he had a team of amateurs interested in collaborations, and that's what it is. So we have me and other 5 astronomers. They're all amateurs, they're astrophotographers. And here are their little babies and their fantastic little telescopes, but they're small, they're 8 inches to 45 centimeters. So it's really interesting to work with this kind of telescopes when I'm used to work with Gemini and with Hubble. So I told them about the sample I had selected. I had selected 3 S0 galaxies that are actually from a gallery of galaxies done by John Hibbert and collaborators that has gas, H1, hydrogen gas outside them. So we know there's something peculiar going on there. So I wanted, they were all observed from the Southern Hemisphere during the summer and the fall 2020. But they are still not convinced that they're going to be able to do anything with this. So I had to convince them to first observe Centaurus A. And as a proof of concept, we observed Centaurus A to the death. So we observed 42 hours of Centaurus A with those telescopes, and we put together the data. And this is this fantastic image where we are able to see shells that the 4-meter telescope sees. So we're very happy with the results. And then when I showed them, I wanted to observe up to 30, and they were like, oh, too small. Maybe we're not going to be able to see anything. And then after 10 hours, here we go. We see shells. We see the shells that Hubble Space Telescope sees. See, this is the image by the Hubble Space Telescope, and this is our image where I have identified the shells there. And here is a shell that's an outer shell that I think is actually present. We just need to observe more hours of ARP-230. So we actually understanding better if ARP-230 is really a merger, and if this is, we can actually do a simulation for that particular galaxy. So here's a conclusion and next steps. We need to get more data for ARP-230. We need to do the other galaxies that are the pilot project, and then we're going to expand the sample. We're going to open it up to all astronomers, amateurs in Brazil to join the collaboration. And then we're going to do follow up with larger telescopes to do their properties and all. So thank you very much. I'll leave you with this beautiful image, and you're welcome to use it in your screen around of your own computer. Thank you very much.
Hi, everyone. Thanks for being here. Today, I want to talk to you about the magnetic field in the galaxy Messier 82, also known as the Cigar Galaxy, and how this magnetic field might be channeling the high-speed material from the starburst core out to several kiloparsecs away. First, the galaxy M82 is extremely luminous galaxy. To put things in context, M82 is approximately 5 times more luminous than the Milky Way, and its core alone is 100 times more luminous than the core of our own galaxy. You know, this high luminosity in the core, it's an indication of large star-forming activity, and it's believed to have been originated or been the consequence of the interaction of M82 with a neighboring galaxy, with the neighboring galaxy M81. Right? When we observe M82 in H-alpha emission, we can see these high, super winds, this high-speed material reaching up to several kiloparsecs away. And furthermore, in infrared, when observing infrared, you can see that these high-speed outflows are pushing away dust into the interstellar medium, right? When the core of M82 was observed with the Sophia Hawk-Plus instrument in the 53 micron band, it was found that the orientation of the magnetic fields is perpendicular to the direction of the galaxy plane in alignment with the outflow, right? But overall, the shape of the magnetic field resembles a little bit the magnetic field of a rain current, in which the magnetic field lines are in the poloidal direction, right? So this particular picture of the core of M82 made us formulate 3 questions. First, what is the interplay? How are the magnetic field and the flows interacting with each other in the core? 2, how does the magnetic field look at distances away from the core, given this picture that we have of the core? And 3, we would like to know if the material that travels along the magnetic field lines will escape the galaxy or not. This is possible if the magnetic field line is strong enough to form close lines, in this form of loops that will facilitate the material to go back to the core, or instead it's open in this way and then the material will escape. In order to answer these questions, we took an approach that can be summarized in 3 steps. First, we needed to calculate the average magnetic field strength in the core from the dust polarization data. And for that, we used the Davis-Chandrasekhar-Fermi method, which basically combines the information from polarization angle dispersion, mass density, and velocity dispersion to calculate a value of the plane of the sky magnetic field. We determined that this value is 1 milligauss. However, like in the core of M82, with the presence of this large outflow, these will indeed modify the value of, or will have an effect on the value of the magnetic field strength. So when you take into account, the value is reduced actually to 0.8 milligauss. Once we had that value, we needed to construct then a map of the magnetic field in the core itself. And for that, we utilized the information from the turbulent plasma beta, which is a parameter that quantifies the ratio of the energy on the kinetic energy in the gas to the magnetic energy, the energy of the magnetic field. The value that we obtain for that, tell us that in the core of M82, the energy of the magnetic field indeed is approximately 2 times the energy of the gas. So finally, the 3rd step in answering this question is a technique that is being used in solar physics for several years, called magnetic field extrapolation, which basically allows to know the magnetic field in the sun's atmosphere by extrapolating from the sun's surface. In order to use magnetic field extrapolation, we need two things. First is to know the magnetic field in two boundaries. For M82, one natural boundary is the plane of the galaxy, in which we actually have measure values of the magnetic field, and the other boundary is at infinity, in which we can assume that the magnetic field vanishes. Then the second thing that we need for the magnetic field extrapolation is to solve and construct a potential field solution. So when we apply this method to M82, then we can extend these magnetic field lines that we see in the core to magnetic field lines that looks like this. These in particular are drawn up to 5 kiloparsecs away from the core, and we see that the poloidal field that we see in the core is extend up to these distances. All right. So if we put this with all the information that we have now with the M82 in this image, right? We want to remember that the presence of these outflows in M82, and we want to know if a particle that travels from the core out at some point will break free from the magnetic field lines. And the way that we can do this is by calculating the energies the same way we did in the core, but at larger distances. So we can choose a distance of 6.6 kiloparsecs away, because we have the magnetic field from the extrapolation, and we have measurements of the gas motion and mass. And then with this information, we calculate the magnetic energy and kinetic energy at this distance, and we find that kinetic energy indeed is larger than the magnetic energy, implying that the material does escape at this distance. So in order to summarize, we go back to the three questions we established at the beginning. First, we find that the starburst core is in close equilibrium between magnetic field and flows. Two, we found in the magnetic field, the poloidal structure that we see at the core really extends to several kiloparsecs away. And three, we find that the magnetic field lines at approximately 7 kiloparsecs away are open, facilitating the escape of the material from the core into the intergalactic medium. So this result actually tell us how, or help us understand how the intergalactic medium will be enriched by the material from starburst and the magnetic field from starburst. And we have to remember the intergalactic medium is the place where new galaxies will form in the future. So for any questions, we can email any of the co-authors. And thank you so much to our the institution that support us, and thanks for listening.
Can you hear me?
Yes, we can, and we see you.
Okay, thank you. Well, first, thank you to NASA, USRA, Sophia, and of course the ANS Press Office for this opportunity. My name is Alex. I'm a NASA postdoctoral fellow at the Ames Center in California. And I would like to start this talk with a very simple question: why galaxies look like this? If we were able to put different galaxies side by side, we would see that they have different sizes and structures. The main galaxy of this talk, M51, it's approximately half of the size of the Milky Way, with only a 10% of its mass. If we compare both of them to the giant low surface brightness Malin 1, who is approximately the same mass of the Milky Way, we start to realize that there is a huge variety of morphologies in the spiral galaxy class. And The reason of these morphologies cannot be just the stellar mass content. It cannot be just the gravity. It has to be something related to how the stars are being formed, what is the past of history of interactions of this galaxy, and so on. But there is also more ingredients. In order to create a galaxy, we need to create stars. Stars are made of compressed gas, but the problem is that to compress gas, we need more than gravity. If it was only for gravity, the clouds of gas would just rotate faster and faster as they compress. So there's an invisible ingredient of the magnetic fields that remove some of the angular momentum. Magnetic field has been detected in the molecular clouds of the Milky Way, like these observations with the Sophia Hawk instrument. And we know that they actually help to shape these filamentary clouds and in the end regulate the star formation. But this is only a tiny patch of the whole galaxy, how this magnetic field looks like at the big galactic scale. Well, earlier in 2020, we saw this amazing picture from Lopez Rodriguez and Sofia team detecting for the first time the magnetic field lines of the spiral galaxy NGC 1068. Turns out that the magnetic fields of the molecular clouds span along across the whole galactic disk, affecting the star formation and even the angular momentum of the gas clouds. This is a striking result because remember that the molecular clouds are very complicated. So it's surprising that we had such a smooth and coherent spiral structure. So at some point we started to consider, can magnetic fields influence the final structure of galaxies? Can they shape them? Well, we know that magnetic fields cannot affect the stars directly, but they can affect the gas before they turn into stars. So we must look at the clouds of gas before they turn into stars in order to find any evidence that magnetic fields may be playing some role in the shape of galaxies. But we know that magnetic fields were in galaxies for almost half a century. Using radio polarization observations, astronomers detected magnetic field lines in external galaxies like M51. So what is different now? The reason is the different types of gas. Thanks to the polarimetric capabilities of Sophia, we're finally able to explore the deepest regions of the molecular clouds in galaxies where the stars are being born. Radio observations are sensitive to a different type of gas, which is the diffuse gas. It's too diffuse to condense, is only detectable in radio, and as opposed to the molecular clouds, does not give us much information about the kinematic conditions or influence of the magnetic field on the stars before they are formed. So in order to answer, do magnetic fields shape galaxies? First, we need to address, is the magnetic fields of the diffuse gas equal or similar to the magnetic field of the molecular gas? All remember, on a galactic scale. So in order to answer this question, we observe the galaxy M51, unknown galaxy observed in synchrotron polarized radio emission for, remember, to detect the diffuse gas, the magnetic field of the diffuse gas. We use the Sophia Hawk instrument to detect the magnetically aligned dust grain thermal far infrared emission of the molecular clouds. But how do you compare two different magnetic fields in galaxies? With one parameter, the magnetic pitch angle. Fields with low pitch angle tend to look like more circular, and fields with high pitch angle, close to 90, they have an appearance of being radial. We can measure this for both the magnetic field and the morphological structure. And this will be the only plot I will show in this talk, which is a magnetic pitch angle profile. The variation of the pitch angle has a different radius for the magnetic field. What we found is that when we make this plot for the radio diffuse gas data, we obtain like the spiral magnetic structure is very uniform with an average pitch angle degree of 20 to 30 degrees. But if we compare this with the molecular clouds, we find that the inner region, the inner spiral for the molecular gas and the diffuse gas is different in the outskirts. So there is a distortion in the outer region of M51 in the magnetic field of the molecular clouds. But that was in the arms of M51. If we go to the interarm, we find no distortion in between arms, with the molecular magnetic field closer to what we saw in the diffuse gas. So what is going on exactly? The galaxy M51A is in reality two different galaxies, M51B, which has been interacting with the main disk of M51A for at least 600 million years. And we know that these gravitational interactions affect to the kinematics of the molecular clouds very profoundly, more than the diffuse gas, because of their ordered rotation around the center of the galaxy. This effect on the molecular clouds tend to compress the clouds of inside the spiral arms, enhancing the star formation. We see a higher rate of star formation in the outer region of the spiral arms of M51. We know that star formation and magnetic fields are related because of this observation that we saw in the Milky Way. So now, the only ingredient that we need to find out is if the kinematics of the molecular clouds and the large-scale magnetic fields can be related somehow because of this stretching of the gravitational interaction with M51B. So I'll leave you here with the conclusions that the main result of this project is that the kiloparsec scale, the magnetic field in the diffuse gas is different from the magnetic field of the molecular gas. This means that we need to review all the conclusions that were drawn in the last 50 years in terms of the effect of magnetic fields in the final structure of stellar disks. This means also that we need more high-resolution far-infrared polarimetry in external galaxies. This is a very complicated and particular galaxy, M51, which has been interacting in a minor merger for some time. We need more galaxies with and without interactions and in different conditions. And as a final conclusion, let's say that the gravitational interactions is triggering an interlink effect between star formation, the magnetic fields, and the molecular clouds. Thank you very much.
Alrighty, thank you everyone for your fascinating talks. We are going to move to the Q&A. Quick reminder to please state your affiliation and who your question is for when you share your questions in the Q&A box. And please, again, remember to share them in the Q&A box instead of on Slack. I'll pass it over to Susanna.
Great. Our first question is from Ryan Wyatt of the California Academy of Sciences. And this is a question for Adi. Wouldn't you expect to see gas and dust ratios correlated in any galaxy? Wouldn't galaxies that have a lot of gas also have a lot of dust and vice versa? And if not, what are examples of some galaxies that are gas rich but dust poor, or vice versa?
Yeah, that's a really good question. And yeah, in general, you do expect the gas and dust levels to be linked. And the ratio of the amount of gas, the amount of dust, may be a function of various things that are specific to that galaxy. For this study in particular, the IR observations, which are sensitive to dust, were the angular resolution of the telescope was quite large. So it was looking at the IR emission across the whole merger. The gas measurements were done using the X-ray observations, and those were looking like really close at the center of these mergers. And so this trend was interesting because it was connecting dust levels that might be more widespread throughout the galaxies to kind of the nuclear gas levels. And this may or may not be saying that gas and dust are easily able to be transported to the center of these galaxies during the mergers. We don't know if that's true because, like I said, the IR observations don't have really the resolution such that you can kind of measure how it's distributed throughout the mergers. So in the future, higher res IR observations will allow us to kind of better understand that nuclear amount of gas and dust.
Great, thanks. Our next question is for Duilia from Jan Hattenbach, who is freelance. He asks, are you looking for more amateurs to participate in your project, even outside Brazil? And if so, what do they need? What requirements, equipment-wise, are there to collaborate?
Great question. Yes, we are looking for a global collaboration. We want everybody to be obsessed with S0 galaxies and early type galaxies and deep images of those beasts. So the requirements are at least large enough telescope that will have a setup of 1 to 2 arc seconds per pixel. So perhaps at least an 8-inch telescope. And also a long exposure capability. And we are using right now a filter that's very common among amateurs called a Luminance Filter. And the Luminance Filter is a broadband filter. And I think it's a little bit of the secret of this project, because it does have this capability of seeing the low surface brightness features outside the galaxies. So yes, more the merrier. Email me and find me on social media, and we are going to put together a network for this.
Great. Next question is from Liz Croisy of Mercury Magazine. This is a question for Alejandro. I may have missed this, but why did you choose to study M51?
Oh, well, that's a great question. Well, M51 is a long-known galaxy in radio polarization observation, so we had available radio data for the diffuse gas. M51 also is quite close and quite bright from the Milky Way, so it allows us to get high-quality data with Sophia Hawking in very little time. But perhaps the more scientifically driven reason is that M51 has been interacting with this in this merger for some time, and it's the perfect example of an extreme interaction. So we can try to find out if there is any difference between the diffuse gas and the molecular gas. So it's M51 was perfect for this purpose, and I think that answered the question.
Are there any plans to look at any other sources?
Yes. In fact, well, we have approved a new program to observe several galaxies in the legacy program from Sophia, and one specific galaxy that's been interacting with some cluster that I hope that the next cycle that we will be able to fly to and observe them.
Is Sophia back to flying yet at this point?
I'm not sure exactly about the timeline, but yes, it is operating and flying.
Great, thanks. We've got a question for Jordan coming from James Urton of the University of Washington. Are there any special characteristics of M82, like its high luminosity, that made it possible to extrapolate its magnetic field? Or to put it another way, would you be able to perform this type of analysis for almost any galaxy?
Okay, thanks for that question. The high luminosity of M82 certainly makes it a great candidate to try to understand every physical property in it. The reason why we started with M82, in my opinion, is because we were able to have due to the distance, we have high resolution data from Sophia. It allowed us to resolve magnetic field orientation with the at the resolution. So we really started, and the other aspect of this is that in order to apply this method, we have to define a very clear boundary at which you have the measurements of the magnetic field to start extrapolation. Sophia currently it's running a legacy survey for Galaxy, and we expect to repeat this and perform this analysis in other galaxies, and including some other starburst galaxy as well.
I actually have a follow-up question for you. What results out of this, were there any that were unexpected, or was this primarily kind of confirming what we thought is how it behaved?
Well, certainly, it's measuring magnetic fields faraway objects like galaxies is a little bit difficult. That's why we only can measure with the Sophia hot plus in the very core where most of the gas is, right? Now, far away from that, there is just not enough gas and polarized dust to make observations. So there was, I think there was an indication based on what we saw in the core of what can be happening out there, especially when you look at the shape, the specific shape of the high speed, wind. That there was definitely something channeling or helping create this shape, but only by doing this extrapolations and actually visualizing the field lines, we can confirm that it is the magnetic field who's helping. It's magnetic field who's creating and facilitating the escaping of the material into the intergalactic medium.
I'm assuming that these observations are presumably pretty consistent with the models that have been created for how this is being thrown out. Yeah. Awesome, thank you. Next, we've got a question from Pak Xing of UC Berkeley. This is a question for Alejandro. The field structure in M51 is quite different from the simple spiral structure of M51. So could it be a result of more complex 3D field structure of the entire galaxy?
That's yes, that's a great question. Well, and then next step in the project will be to of course, we found out that there was this difference between the different regions of the magnetic field. Next step, of course, is to try to model and shape the forces that may be applying over the different regions of the ISM. That we know that the merger M51 is probably not perfectly aligned with the disk of the main galaxy. So yeah, that's a very important thing that we need to take into account for the modeling the 3D field structure in the end, and simulate the forces that may be applying in the spiral arms, and what techniques like those apply with like those that presented Jordan here in the talk, and will be very helpful for this.
Great, thanks. That is all the questions we've got in the Q&A right now. How are we looking in Slack?
No questions in the Slack, just some handy resources associated with the briefing.
Great, we can give it another minute or so and wait for any questions to come in.
In the meantime, I'd like to ask one. This one's for Jordan and Alex. I'm seeing a lot more results coming out across almost all fields within astronomy related to magnetic field measurements. When I was back in grad school, magnetic fields were rarely talked about. They were kind of ignored. But it seems that they play a very significant role across virtually all kinds of astrophysical objects and phenomena. And I'm wondering if you guys can comment. You've alluded to you've explained the importance of the magnetic fields in these two galaxies, and also that it's pretty hard to measure magnetic fields for more distant ones. But I'm wondering, some thoughts on the importance of the relevance of magnetic fields in astronomy.
Jordan, you want to go first?
Sure. So, yes, certainly, to quote one of my authors, John Schmel, quoting somebody else, basically, there are some phenomena that can be observed, and it just basically cannot be explained with just hydrodynamics. So I think she said something about hydrodynamics is just not gonna cut it. So magnetohydrodynamics is actually what will explain some of the phenomena that we observe. I come from the solar physics group, in which magnetic field, the solar physics field, in which the magnetic field is something that has been dealt with over and over for several decades, right? So I came a lot with the mentality of we really should be quantifying magnetic field as much as we can. And fortunately, it is recently observatories like SOFIA have been coming up with data that has allowed us actually to apply techniques in advanced statistical methods to actually, you know, to have more information about the magnetic field, because it is necessary to explain some of the phenomena we see.
I might add some words. Well, I would say that one of the main problems is that it's really hard to get to have the quality data, to get to know some of the structure of the magnetic fields. I mean, M51 is, for example, a galaxy is really close. We have high quality data after many hours observing with SOFIA, and this is things that they are able. We were able to do it now for the first time ever. So I think that steadily, hopefully increasing, we will be able to see more high resolution data and deeper data. Of course, I come from myself from deep imaging, and I'm closer to the presentation that Duilia made in lenticular galaxies, and we always want to go deeper and deeper because the galaxies don't really end. And something that's very important is that from observation that we have is that magnetic fields may be playing out way more an important force in the outer scales of galaxies, and we know nothing about this, nothing at all, because it's just too hard. We don't have enough. If we were able to have a giant SOFIA flying in the sky, we'll be able to see this. But it's really hard. So it's a whole world that's completely hidden to us in this magnetic field side of the galaxies.
I'm also quickly a true believer that we should demystify the magnetic field in astrophysics. It is hard, but it can be done.
We've got another question in here from James Urton of University of Washington again. This is a question for Duilia. Is there any relationship between the dust shells that you're detecting and the formation of stellar streams like those found in the Milky Way after a galactic merger?
Yeah, it's a slightly different process, but it's all about interaction between a galaxy and the tidal force, right? So when we look at the shells, they are really kind of concentric into the galaxy. So they really have this particular shapes outside. It's almost like throwing a pebble in a pond, right? When we look at the tidal streams, they are more like the distortion of the arm of the spiral galaxy, or a small galaxy that has been distorted and is being incorporated inside the big galaxy. So it's a little bit different, the type of collisions there. But yes, the deep images that we have been taking and other people have been taking shows the streams. They are the stellar streams like the ones in the Milky Way are very important that we go deep to detect those.
Great, thanks. And we've got a couple of comments in the Q&A box now. Joan Schmeltz has pointed out to me, answered my question regarding what was new, specifically unexpected about this. And she's saying that the wind could have looped around and come back to the galaxy, like in the solar corona, but instead it channels out into intergalactic space. So that's interesting that models haven't included magnetic fields before. I feel like I need to go read up on this now. And Garrett Virtue says, the Hawk Plus instrument is one of the most significant advances in astronomical instrumentation in decades. To see magnetic fields in such detail boggles my imagination, which I completely agree with. It's kind of amazing.
Yes, it is.
That's everything we've got in the Q&A box at this point.
I have one more question, if I may. This question is for Adi. We've heard some talk at this meeting about nanograv and its effort to detect the stochastic gravitational wave background from supermassive black holes that are interacting. And you've now presented multiple examples of not just double black holes, but also triples. And I'm wondering, does that complicate the search because the stochastic background could be, including frequencies that haven't been considered in the modeling and the analysis, given these multiple interactions among multiple objects?
Yeah, so that's a really good question. So for the little simulation that I showed you on my slide, that was very specific to a system where your two supermassive black holes in the center are very close to one another, and that third supermassive black hole is pretty far away. And so in that case, if that third supermassive black hole, that perturber is helping merge those two, its gravitational wave signal probably won't be very strong with respect to the two in the center. I do think, though, that when nanograv eventually does have a lot of results that they can start fitting with models, the rates that they calculate by fitting their data to models, so the rates of how many binary supermassive black holes are actually merging, can then be linked to the rates of how many perhaps triple systems we expect. And I think that might give us better insight onto how many of these systems may actually be driving the signal that nanograv will be seeing.
Yep, looks like we've got one more question in. Another question for D from Ethan Siegel of Starts With a Bang. In general, if you have roughly as much baryonic mass between two post-galaxy merger supermassive black holes as the masses of those supermassive black holes themselves, wouldn't you expect violent relaxation to lead to a merger?
So the dynamics of the two black holes as they start moving very close to one another starts changing as, like you said, the mass between the two supermassive black holes starts changing. So at the beginning, dynamical friction is the main mechanism that's driving the two black holes closer to one another. But with time, tidal forces actually throw out a lot of the gas and the dust that's in those galaxies. And when the two supermassive black holes do get close enough to one another, such that they're gravitationally bound, for example, you don't actually really have a lot of that galaxy's mass there anymore. And so at that stage, the main mechanism of energy loss changes from dynamical friction into them actually having three-body interactions with nearby stars that they can kind of grab energy and angular momentum from. And so, as you may or may not know, that leads to a lot of problems down the line, or so we believed, for how do these things eventually merge if they don't have enough gas, or if they run out of gas and things to accrete from. And so I don't have to get into it, but there are a lot of now ways that we've thought of for them to continue moving closer to one another. But it was an issue in the past, though, thinking about, well, what happens when a lot of the gas and the dust is flung out because of tidal interactions? How do these two things continue losing energy and moving closer to one another? Hopefully that answers your question.
Great, thanks. That's it for the Q&A.
Alrighty, I think we are actually 1 minute over. So feel free to continue questions in the Slack and chatting with the speakers. I just wanted to thank all of our panelists today for their wonderful presentations, and thank the audience for their really great questions, and thank all of you for coming. Thank you to the PIOs who helped with the press releases and briefing prep. Our next press conference will be at 4:30 p.m. Eastern, and will be titled Evolving Stars and Nebulae 1. So thank you all for coming, and I hope to see you at the next press conference.
Thank you.
Thank you all. Bye-bye.
Thank you.